Am I good? All right.
So, Gregory is telling us more about modularizing CPU semantics. So, go ahead, please.
Thank you. All right, so you guys all probably saw Peter's talk this morning about the grand vision of verifying a hypervisor. My grand vision is similar in many respects. So virtualization is this technology that we use to run multiple machines on the same core or on the same computer. In the same way that we run multiple processes on the same operating system. And we can provide a lot of things basically in the exact same way that, the exact same sort of features that operating systems provide to processes. Obviously, to provide these additional features, you have highly privileged code that has a great amount of visibility into both your process and adjacent processes, or in this case. And this came out, I think, 2 days ago. These things are vulnerable, and it's a big deal because these things underlie a lot of infrastructure that you use every day. All right, so our goal is to prove this little stack correct. It's not really little, but in the picture, it's not too imposing. And the property we want to prove is let's see. No, that doesn't work. Okay, the property we want to prove is a refinement specification. So we want to be able to show that if we run 3 guests on top of our implementation down here, that our implementation will act in only ways that those 3 guests could have acted if they were run in parallel, connected by these little green network things. All right, and for the purpose of this talk, I'm just going to talk about one of these VMMs. That'll be the middle one, but they're all the same, so it doesn't matter. All right, so the outline of this talk is I'm going to tell you a little bit about what the computer looks like from the hardware point of view in a less scary way than Peter did. And it's going to, so we'll talk a little bit about that. Then we'll focus on the CPU, which is exactly what Peter focused on, because it's probably the most interesting piece, but by no means the only complicated piece. We'll talk about how we decompose the semantics, which will align with a great deal with what Peter told you this morning. And then we'll tell you a little bit about how we're aiming to use this decomposition in our overall proof. All right, so if you look at computers from the system level and not from the program level, you'll see all these additional things. We're used to thinking about the CPU itself down here, but there's also things like interrupt controllers and devices. Now in the specification, you might have 3 CPUs and 3 devices, but in the implementation, you'll have 3 CPUs, but some of your devices and things like that might be software virtualized. And so these things that are marked as blue are things that are actually implemented in software and then exposed to the higher level piece as if they were virtual hardware. And as I mentioned, we're just going to talk about this one little box, or this one little refinement over here. All right. So Peter gave a great overview of this. So some of my slides are a little bit redundant, but I'll go through them anyway. So down here, the specification we want to do is we want to connect the specification down here. This is the implementation. So this is going to be ARM running with full virtualization extensions. So an ARM VA, ARM8 A class processor. And up there, we were going to have ARM kind of without virtualization extensions. So we're not going to support a feature called nested virtualization, which would allow you to run a hypervisor inside of our hypervisor. It's just not necessary for our use cases. And the way we describe this, so that I can fill these boxes with more than just English text, is a combination of 2 things: the instruction semantics, which Peter showed you quite a bit about, and the concurrency semantics, which is kind of how these things get interleaved. And for the purpose of this talk, I'll say that that's ASL and this concurrency semantics down here, kind of linked together by this this guy runs this guy sort of thing. And we can do the same thing at the top, but we're just going to specialize that ASL semantics to not have EL2 logic in it. So we'll just be removing some of it. It'll be a smaller semantics than this, but not that much smaller. All right. And so the normal way we might do this is we might implement a VMM using some software and some hardware. But the problem with this is that this exact implementation isn't great from our point of view because we want a little bit more functionality in our user space than what PKVM is aiming for. So instead, we break this full refinement into 2 pieces. One is this thing down here, which is a microkernel called Nova, it's like an operating system or a hardware abstraction layer, and it provides the ability to run user space programs as well as hardware virtual CPUs. And then a C++ program, this VMM up here, which will run in user space and provide all those extra things like the software emulated devices and things like that. Now the semantics of these two blue boxes is very similar to the semantics down here in ASL, but there's differences. So all of the unprivileged logic is going to be very similar, but all the privileged logic will be different. And what our goal is to do is to factor those semantics so that we can use one thing for all the common pieces and then just tweak the other box. So basically we're going to introduce an abstraction layer that allows us to run the same program under different interpretations to fill in different pieces of these boxes. Right, so this is how it works. This thing over here is the unprivileged code. That's what you'd get from ARM, with everything kind of linked together. And what we're going to do is we're going to draw this line here, and we're going to pull some of the code out into this box down here, which is what we're going to call the privileged code, so that all of these blue boxes are exactly the same. And we'll be able to change these boxes, whether we're running guest CPUs, guest code, host code, or on the physical machine. And the nice thing about this setup is that once I've done this decomposition, the top two layers of this box, SASL plus EL1, running on top of the concurrency semantics, in the specification is exactly the same as it is in the implementation. So the idea is that this will allow us to factor the proof when we're running in hardware virtualized mode to be relatively easy by construction. And the key thing to think about here is the gap between what the actual specification is, the red box, what's written in the ARM manual, and the blue box, which says our decomposition of it. So that's the focus of this talk. That's what I mean by decomposing CPU semantics. All right, so I've got a few little examples. Some of these are more realistic than others, but this is some of what Peter was talking about this morning, so a little bit more code, maybe a little scarier. This is an instruction in ARM that reads TTBR0EL1, which is the page table root at execution level 1, so operating system mode. And this is what you'd get if I think this was copied out of the one of those many web pages that tells you the semantics of what these instructions do. So what we have to do in order to decompose the semantics is we have to identify what the privileged state is. Now we're at EL1 here, so we should have access to all the EL1 registers. But you'll notice that to compute the answer even when you're at EL1, you need to look at some EL2 state, which is hypervisor state. And we don't want to expose that state to the unprivileged logic, because then we won't be able to intercept it. We won't be able to know that these checks are being executed correctly and things like that. So we decompose it, and we end up with this relatively simple unprivileged program here. And then this slightly more interesting handler, which does all the checking of EL2 and just returns the appropriate value of TTBR0EL1. And so using kind of regular old functional programming language equational theory, you could see that if you were to link this program with this program and then do all the normal jump threading and whatnot, you would end up with something akin to this program over here with the gray pieces already highlighted out. All right. So that tells you a little bit about what it looks like when you have some interesting control flow. The more interesting thing, and that happens all the time, is actually memory accesses. And this is the memory instruction, LDUR reads, does a read of memory. And I think Peter actually showed this mem relation on his slide, or this mem function on his slide, and told you that it does things like splitting accesses and doing address translation and all that. And so we focus on that piece. The rest of it is completely unprivileged. And, excuse me, we can rewrite this bottom piece. We can meet essentially the same interface, but basically all of this stuff occurs in the unprivileged mode. So you ask to translate the address, then you ask to read the address. And the nice thing is that this address here, the unprivileged logic is only ever going to see virtual addresses. It's not going to see the actual physical address. So we'll be hiding that from the unprivileged logic. And we'll also be guaranteeing that every time you do a memory read, you'll be accessing the virtual address and we'll be able to show that the translation is done correctly anatomically. All right, so this memory interface looks like translate an address, which gives you this handle and some information about the permissions, so the permissions can be checked. But then you also have read and write, and the permissions and the address translation is validated again using this handle inside read and write, and that ensures things like TLBI flushes and whatnot are like that the unprivileged semantics is not using very old translations to continue to read after those translations were invalidated. All right. I don't know how I'm doing at time, but okay. There's not even a timer for me. This is wonderful. Okay. All right, so I told you a little bit how we decompose these semantics, and we're basically at this. So I told you that this simulation relation over here for when we're running with hardware virtualization. So we're not running our C++ program. We're actually running a core, and ARM is doing the virtualization for us. Is relatively easy. I'm going to give you an intuition for what this simulation looks like and what we end up having to prove in our overall proof. So you imagine you're just starting the computer, you have a register file, but you haven't started executing any instructions yet. Effectively, we're going to say that the implementation and the specification have the same pipeline state. Okay, the registers are the same, and there's no speculation or anything like that going on right now, so the pipelines are in exactly the same state. So those will be in our relation ARM. As we start executing, we're going to assume that ARM got virtualization correct. And so if we take a step in the unprivileged logic, the unprivileged semantic says, move register R1 to R2 or something like that, then that will go, it'll start advancing the pipeline state. Maybe we were fetching new instructions or whatnot, but those will be similar as long as we're staying within the CPU itself, okay? So these aren't things that hit memory or anything like that. Now, we'll run along, and at some point, we might realize that in the implementation, there's a fault because, for example, second stage address translation said you're not allowed to read this page that you're trying to read. But in the specification, there's no fault because we're emulating a regular machine that has no second stage translation. So in this case, the relation is going to relate the implementation, which is basically one step ahead, one faulting step ahead of the specification. And we'll be able to quantify exactly why that fault occurred using this red box or this red circle. When we continue to run, we might get to a point where that red circle is the next thing to do. We need to take this exception, and in that case, our Nova kernel, the microkernel, is going to take that exception. It's going to transfer control down into Nova, and then transfer it back up to our VMM. And now our VMM has two choices. One thing it could do is it could roll back the semantics, so despeculate that, maybe fix up permissions in the table. Maybe you're doing a lazy paging or something like that. And then just start again and say, try again, I think I fixed the problem for you. The other choice it could do is it could actually try to emulate the instruction, which is necessary when you're talking to software virtualized devices, for example. And we could try to finish it by using information that's expressed in this fault called decode assist registers. Ultimately, either one of those that we do, the obligation we need to do is we need to get back into a state related by R, and the only way you can enter virtualization mode is if you're in an architecturally stable state. So both of those transitions, either despeculating or finishing the instruction, will get us into appropriate states there. So that's basically the end of the talk. I walked you through our idea for decomposing CPU semantics, which aligns very well with what Peter and company are working on, and how we're ultimately trying to fit this semantics into the overall proof of this bare metal property, the specification for our virtualization stack. So that's it. I'll take questions now.
So questions? Dominique?
Just to make sure I understand correctly, so what you did is you took the original ASL spec and you manually rewrote it by separating out these two pieces, and then you established, then you worked with the rewritten spec and proved a simulation between running on a isolated machine and running in a VMM.
That is effectively correct. Well, I'll have you, like, what I've presented here is our proposal for how we aim to do this. We have done this with several instructions and kind of given an argument for how that fits into the proof. So the VMM is quite large, and we've verified quite a bit of the C++ code. And we have this question, what is the specification for now start running in the hardware? So what we've been doing with this is kind of doing on paper that decomposition for several instructions, kind of identifying the interface between the hardware and the software, and then doing some proofs about, when this fault is taken or when memory is executed, how does that integrate with the software iris invariants and whatnot that we have.
Right, and so this rewrite of the ASL spec into a different form, have you proven anything about that rewrite, or is that not part of the goal? Is it? That
is part of the goal. The degree at which we've done it is kind of what's expressed on these slides. So we've done this for various instructions and argued kind of informally on paper, but not in a mechanized sort of way yet.
Very interesting. Thank you.
Sure.
Other questions? No, we have plenty of time actually.
Okay.
So, yeah, I just wanted to reiterate on, I think, this one. So you come up with this splitting, let's say. How? Manually, or, because if you want to do that for all the ARM instructions, then...
Yeah, so ARM is let's say, slightly more sane architecture than other architectures. And, Peter mentioned that there are an enormous amount of, the semantics is very large, but relatively little of it mentions privileged state. So there's lots of instructions that are completely unprivileged, like add and whatnot. We believe we don't have to do anything to those. But there are, there's still things like memory accesses and maybe 100 MSR registers. To do this kind of in an automated way, you'd probably want to do something like taint analysis. So you could look at this original program, identify any paths that are influenced by state that's outside of the privileged component. So this would be EL2, for example. And that would be able to flag for you the places where you need to abstract. Whether you could do that abstraction completely automatically, maybe you could in some instances. Like this one I could imagine maybe doing. Other ones maybe a little bit less. Like the memory one is quite subtle.
Yeah, I was also thinking about, because if you think about, I don't know actually, but my guess is that you may have non-trivial, it's not easy to identify, I guess, I don't know, but it seems not so easy to identify exactly which has to do with, control flows that has to do with privileged state and whatnot, right?
Yeah, I think I'll speculate it might not be terribly difficult, but I'm not sure. We know which variables and whatnot, like which pieces of state are privileged, so it's a matter of doing a taint analysis.
So I think that's the ground truth. I was thinking about maybe the manual says, oh, this is not privileged, but then it touches something which is.
We can determine what's privileged very, very clearly by looking at what state is controlled by EL2 and not visible to EL1. So we have a very mathematically rigorous way to determine that.
Okay, yeah, that's fine.
So something I'm not seeing. So how do you connect your code is mostly written in C or C++, I think. So how do you connect the ASL state or the ASL representation of architectural state to the C++ state? Or to the way you access this ASL state from C++? I guess you have some way of doing that.
Yeah, so let me see if I can. All right, so here, what happens when you take a fault is in the architecture you transfer control to the hypervisor, and that writes state into some memory blocks. Those memory blocks get copied up into software selectively by Nova, and then software handles what's going on, and then software will write data back, and Nova will copy that information back to this state as well. Does that answer your question, or not quite?
No, you were talking about, I think, the implementation of Nova in C++, right? And that's the part you're verifying in C++.
Both Nova and the VMM are both implemented in C++. In this talk, I just talked about the VMM, the verification of the VMM. And in that case, we have a specification for what it means when, if you stay for the next talk, not in the next session, you'll hear more about this, but what exactly is the specification for what happens when this thread faults due to a memory access fault or a privileged state access fault or something like that. And that gives us a specification for what we'll know basically at the beginning of this function and what we'll need to establish at the end of this function. So then this becomes a standard C++. You don't have to worry too much about hardware except for the fact that it's running concurrently with you.
Right. And do you have some way of connecting? So you have specs then? So do you have some way of like, you use these specs on the C++ verification side? Do you have some way to connect them to the ASL view on things, or?
Yeah, that's done because the Nova specification is expressed in separation logic. So the state, the register state of this thread running, this hardware thread running, is a separation logic assertion. We can say its state is currently this, and that state includes all of this, things like speculation. You might be speculating this. You might have this register has this value at the first green box and this value at this other green box, and that. But the nice thing is that we're not proving programs that run in the guest. We're focused on running and proving the VMM, so we just treat it kind of as a black box. That's the nice thing about the simulation. Because that simulation is lockstep, we don't really care how it's constructed. We just care about how it interacts with the outside world.
Okay, thank you.
No problem.
So I guess time's up.
Peter has a question.
Very fast one. Yeah.
Very fast or very last?
Both, I think.
Both, yeah.
So that might be a problem. So we talked a lot this week, and that was great. And I think I have some clue what you're doing that I didn't before. And it may be that the answer to this question is not very fast, but somewhere there has to be a proof that your sort of local reasoning of the C++ is soundly gluable onto all of this, right? So somewhere there has to be some proof that if you're using the operational model, that all that excessive amount of potential interleaving can soundly go away. And I think I still don't understand where you imagine that piece of the proof goes.
Time constraints. But what I can say is that, so we're assuming we get to use C++ reasoning when we're reasoning about our C++ code. And the state that the C++ touches and the state that the guest can touch is very independent, with the exception of very specific points, which are, I believe, done with special operations. And those special operations get interesting specifications. But most of the C++ code just has regular specifications, if that makes sense.
All right.
If not, we might need to take it offline.
Yeah, my question is sort of, how do you know that that's a sound way to argue? But we should talk about that some more later.
Absolutely.
Okay, so let's thanks Gregory again.
Thank you.
And